So the goal of my lecture is to explain this picture. So by the end of my talk, I hope actually you know what this picture is supposed to mean. Okay, so there's a little girl and traveling somewhere. So we'll discuss possible closures of a Euclidean line in various geometric spaces. So we'll imagine this Euclidean traveler. So by Euclidean traveler, I mean a traveler who is supposed to travel only along Euclidean lines. Okay? And then she's going to visit many different geometry worlds. And then the question is going to be, what places does she get to see in each of these geometry worlds? Okay? So this is her itinerary. So in 1884, so she's going to travel to Euclidean torus of dimension n at least 2. And her guide, her travel guide is Kronecker. And about 50 years later, she's going to travel to a closed hyperbolic surface guided by Hedlund. And another 55 years later, she's going to travel to a closed hyperbolic manifold of higher dimension guided by Ratner. And then in this new century, she's going to travel to hyperbolic manifolds of infinite volume. So this is her itinerary. So before she travels, she starts on a serious journey, so she needs some exercise. So she's going to do this warm-up, jumping on the circle. Okay? So by the circle, I mean simply the unit circle in the complex plane. So this is simply the set of complex numbers of modulus 1. So you have this unit circle. But I also consider different model, r by z. So this is quotient of the real line by integer z. And these two models can be identified by the map. So if I have a complex number of modulus 1, so every number can be written as e to the 2 pi I x, okay? And x is a real number. And then the map e to the 2 pi I x goes to x. So this gives the identification of this multiplicative model and then the additive model. So I'll think of the circle in two ways. So now for every angle theta, so we are going to denote by r sub theta the rotation by 2 pi theta. So in the unit circle model, so the map just maps z to z times e to the 2 pi I theta. Okay? So you rotate by 2 pi theta. And in the additive model, so this is simply you add theta. So x goes to x plus theta, but of course modulo z. So now you pick any point x on the circle, and then we'll consider orbit of this point under the iterations of this rotation by theta. Okay? So imagine she's standing somewhere on the circle, and then she jumps by 2 pi theta. Okay? And then we want to understand what places she's going to see. What is the closure of this orbit? So if theta is rational, then clearly she's going to actually come back to the same place after finitely many steps. So if theta is rational, right, you rotate by rational angle, and then you come back to the same place at some point. So orbit is going to be closed and periodic. And then if theta is irrational, then you never come back to the same place by rotating 2 pi theta, and then another 2 pi theta, and so on and so on. Okay? And then moreover, it's going to be dense. So the theorem is that if theta is rational, then any orbit of this r theta on the iterations will be closed and periodic. Or if theta is irrational, then the orbit will be dense. Okay? So this is theorem. So from traveler's point of view, you can think like that. So she starts on a circle, and then if she keeps jumping by 2 pi theta, either she's going to see only finitely many places, or she's going to see everywhere on the circle. Okay? So now, okay, so she travels the 2 torus. So 2 torus is simply a product of 2 circles. So S1 times S1. And we can also think of that as the plane R2 quotient by the integral lattice Z2. Okay? So since she's a Euclidean traveler, so I have to tell you what is a Euclidean line in this torus. Okay? So in the plane, we know what a line is. Okay? I have a plane. So I think of a line as a line actually passing through the origin. And then now let's consider the quotient map going from R2 to T2. Okay, so I denoted by pi. So pi is a quotient map from R2 to T2, which is R2 by Z2. And by a line in the torus, I simply mean a projection of a line in R2 via this projection map. So this is my line. Okay? So if I have omega 1 and omega 2, here the point here. So I'm going to denote by L sub omega 1, omega 2. It's the projection of the line passing through the origin and this point omega 1, omega 2. So I have this line, and the projection of this line is what I'm denoting by L sub omega 1 and omega 2. Okay? So now let's imagine she travels along this Euclidean line on the torus. So we want to ask, so which places is she going to see? Okay? So it is useful to think of this unit square. So this unit square is the fundamental domain of R2 over Z2. So fundamental domain for the torus. And here you see actually two vertical lines labeled by A, and then two horizontal lines labeled by B. Okay? So we identify two vertical lines labeled by A by the transformation, just by translation by 1, 0. You translate by 1, 0, and then you identify. And then you identify two horizontal lines by the translation 0, 1. Okay? So I denoted by tau sub A, the translation by 1, 0, and tau sub B, translation by 0, 1. So these are called side pairing transformations. Okay? So when you identify this, the pair of sides according to the labels, we get this torus. Okay? So now you can think of her journey along this line in the following way. So she travels along this line, and then she's going to, when she reaches the boundary of this fundamental domain, so this will be exactly the point 1, the slope of the line, omega 2 over omega 1. And she's going to instantly move back to the y-axis by the side pairing transformation. And this point is going to be 0, the slope. Okay? And this side pairing transformation also moves this line to a new line, but with the same slope. And then now she travels along this new line. And then the same. So when she reaches the boundary, she gets instantly moved to y-axis, and so on and so on. She continues like that. So now if you try to see actually which places on y-axis actually she's visiting, these are exactly the integral multiples of the slopes. Okay? And from her exercise, she knows that if the slope is rational, then she's going to visit only finitely many places. And that means that here actually her trip becomes periodic and closed. Okay? And then if the slope is irrational, she's going to visit all the places in y-axis. So that means that her trip here becomes dense. Okay? So this is exactly Kronecker's theorem in 1884. So any line in the two torus is either closed and periodic. And this happens exactly when the slope is a rational number. And otherwise it's dense. Okay? So she's going to either see a closed line, or she's going to see everywhere in the torus. So now we move to the higher dimensional torus. Okay, so by higher dimensional torus, t to the n, we mean by r to the n divided by the standard integral lattice Zn. Okay? So again, the line is defined in the same way. So in the Euclidean space Rn, we know what a line is. And then by a line in the torus, I simply mean the projection of a line in Rn to Tn by this standard quotient map. Okay? So again, similarly, so I denoted by L sub omega 1 to omega n for the projection of the line which passes through origin and then this point, omega 1 to omega n. Okay? So now actually the situation is different from the dimension 2 case. So dimension 2 case, we had this dichotomy. It's either closed or dense. But in higher dimension, so we can have actually the subtorus of intermediate dimension, like in this picture. Okay? And then if she started actually her journey inside this subtorus, she will never get out of this subtorus because the closure will be trapped here. Okay? But nevertheless, actually, that's the only possibility. So that's exactly the Kronecker theorem. So the closure of a line is always some subtorus of t to the n. And also the dimension of this subtorus is exactly the dimension of the Q vector space spanned by these points, omega 1 to omega n. Okay? So we can consider slightly more general torus. So instead of looking at Rn divided by the standard integral lattice, so we can also look at any co-compact discrete subgroup of Rn and then consider its quotient. So by co-compact, I mean the quotient is compact. That's what co-compact means. Okay? So that the quotient of Rn by gamma is a compact torus. Okay? So indeed, actually, it's not very hard to see. So such a discrete group is always the z-span of n linear independent vectors. So gamma always looks like z-span of n linear independent vectors, v1 to vn. And then we just replace the zn by this gamma, and they have the same picture. Okay? So then, yeah, the theorem is slightly general. So for any n-dimensional torus where we allow gamma to be any discrete co-compact subgroup, and then you consider any Euclidean line, which is simply, yeah, the image of the line under the quotient map, then the closure is always a subtorus, meaning, so subtorus means that you have some linear subspace V, and then the subtorus means that it's a V quotient by intersection of V with your original lattice, and this has to be a lattice in V. Okay? So this is what subtorus means. And moreover, actually, we don't have to insist our line actually passes through the origin. So this problem, we can actually allow lines which do not pass through the origin. Okay, so not necessarily passing through the origin. But in that case, in our answer, we have to allow translations because this subtorus is not going to actually coming from the linear subspace, but we have to allow translations. Okay? But these are all the possibilities. Okay, so now she's ready to travel to a closed hyperbolic surface. So the closed hyperbolic surface is going to be a quotient of a hyperbolic plane. Okay? So I first explain what a hyperbolic plane is before I talk about closed hyperbolic surface. So I'll just use a very nice up-half plane model for the hyperbolic plane. So a pop space model or a pop plane model is simply this. So we consider the plane R2, but we'll only consider the upper space. So it's a set of xy with y coordinate positive. Okay, it's just the half of the plane. But note that we don't include actually the x-axis. So y is strictly positive, so it's the open up-half space. And hyperbolic metric is given by the Euclidean metric, so square root dx squared plus dy squared, but divided by the height, Euclidean height. So y is the height, yeah? So here is my hyperbolic plane. So the meaning that actually the hyperbolic metric is the Euclidean metric divided by the height means that, so if I have 2 points which is very near x-axis, it means that their height is very small, the y height is very small. Then it means the hyperbolic distance between these 2 points are much larger than what we see, okay? Because to compute the hyperbolic distance, I divide by height, and if height is very small, then means distance become very large. And also similarly, if I have 2 points very high above, then their hyperbolic distance is much smaller than the Euclidean distance because I divide by height, okay? So in this hyperbolic plane, so so-called hyperbolic lines or geodesics, so meaning that they are distance minimizing curves, so they look like either they are vertical lines or they are semicircles intersecting the boundary orthogonally. So this means that if I want to travel from P to Q in the fastest way, then you have to travel along this semicircle. Okay, intersecting the boundary orthogonally, or if you want to travel from this point to P and Q, which lies on the vertical line, then you have to travel along this line. Okay, so this is the meaning of geodesics. Okay. So here is another very nice model of the hyperbolic plane. So this model is called the Poincare disk model. So in this model, so as I said, H2 is simply the open unit disk. So we have this x squared plus y squared less than 1. So again, this is disk, but open. It does not include a boundary. And the metric looks like something Euclidean metric, but you divide by this quantity, which means that if you have 2 points very close to the boundary, then they are much larger than the Euclidean distance. Okay? And in this model, geodesics are either the lines passing through the origin or the semicircles intersecting the boundary orthogonally. So these are geodesics, this model. Okay, so now what is the closed hyperbolic surface? So closed hyperbolic surface is by definition is the compact hyperbolic surface without boundary. So you say it's a complete compact hyperbolic surface. So it's a compact hyperbolic surface without boundary. I mean, clearly H2, the above space is not compact, so it's not closed hyperbolic surface. Okay? So how does a closed hyperbolic surface look like? So recall that Euclidean torus was the quotient of the plane R2, the Euclidean space, divided by discrete co-compact subgroup of R2. So this is how we obtain the Euclidean torus, right? R2 is divided by Z2, or more generally, R2 divided by discrete co-compact subgroup. So we would like to say that a closed hyperbolic surface is the quotient of hyperbolic plane divided by discrete co-compact subgroup of H2. So this will be very analogous to this torus case. However, the problem is that H2 is not a group. Okay? H2 is not a group. There is no group structure. So this sentence does not quite make sense. So what is the discrete co-compact subgroup of H2? However, H2 is actually very, very close to be a group. So we'll see H2 is almost the same as its isometry group. Then this sentence will make sense. Okay? So what is the now isometry group of H2? So the isometry group of H2, this hyperbolic plane, is this very familiar group PSL2R. So 2 by 2 matrices with the real coefficient of determinant 1, a quotient plus minus 1. So to see why actually the PSL2R is isometry of H2. So by the way, isometry means that it's a transformation which preserves the metric. Okay, that's what isometry means. So to see why PSL2R is an isometry of H2, so I have to talk to you what is the action. How do I think of this element as a transformation on H2? And it is this linear fractional transformation action. So if ABCD is an element of PSL2R, and then, so this time I'm going to think of H2 as the half of the complex plane. So H2 I presented you as the half of the Euclidean plane, but it's for this definition, it is convenient to think H2 as the half of the complex plane. So point here will be x plus iy, and then with positive y. And this action is just the linear transformation, linear fractional transformation action. So ABCD maps Z to AZ plus B over CZ plus D. Okay? And because ABCD are real numbers, so if Z has positive imaginary part, then you can see actually the resulting complex number will also have a positive imaginary part. So this really gives an action of H2 to H2. Okay? And we can also check that actually from the determinant 1 condition. So this indeed preserves the metric, hyperbolic metric. So every element of PSL2R is indeed isometry of H2. And moreover, it turns out that PSL2R is precisely actually the group of full orientation preserving isometries of H2. Okay? So now, so now I just talked about the action of PSL2R in this pop space. So now let's think about this point I, the pure imaginary number. Then the orbit of this I under the action of PSL2R will give you actually all of H2. It's easy to see from this section. And moreover, you can compute what is the stabilizer of this point I. So you can just compute what's the stabilizer of I, and then it is exactly this rotation, SO2. Okay? So this gives the identification of H2 with the quotient of PSL2R by SO2. Okay? So every point in H2 is the quotient of PSL2R mod S2 because PSL2R acts transitively with the stabilizer SO2. So you see actually, so H2 is the quotient of its isometry group divided by SO2. So this is what I meant by H2 is almost the same as its isometry group because SO2 is this small compact subgroup. So up to this compact subgroup, H2 is equal to its isometry group. So now I can go back to the definition of a closed hyperbolic surface. So closed hyperbolic surface is indeed quotient of H2 by gamma, where gamma is any discrete co-compact subgroup of its isometry group, which is PSL2R. Okay, so this is the closed hyperbolic surface. Okay, so this is the definition, but okay, so, of course, the natural question is that does there exist any closed hyperbolic surface? Does there exist any discrete co-compact subgroup PSL2R? Okay. So I give you one explicit example using the unit disk model here. Okay. So here my disk, so this is the pop plane model. And here I try to draw the regular octagon. So you have here octagon, and then the inner angle is pi over 4. And here you have 4 labels, A, B, C, D. And then when you actually glue this pair of sides with the same labels by the side pairing transformations, we obtain actually exactly this donut with 2 holes. Okay? So more precisely, so here I see actually 2 sides with the label A. Okay? And then, so I told you actually in this unit disk model, so the geodesics are semicircles which intersect the boundary orthogonally. So you have to understand all of the sides are part of the geodesics, hyperbolic geodesics. Okay? And then for each pair of sides by the same label, there is an element of PSL2R which moves this side to that side. Okay? So that's what I denoted by gamma sub A. So this is a side pairing transformation. And then similarly, I have gamma sub B and gamma sub C, gamma sub D. Okay? So the group generated by these 4 side pairing transformations, actually, it is a discrete co-compact subgroup PSL2R. And then the quotient H2 by gamma is exactly what we obtain by gluing this size according to the labels. And then we get this hyperbolic surface, which looks like a donut with 2 holes. Okay? So topologically, any closed hyperbolic surface is always a donut with at least 2 holes. Okay? And conversely, moreover, so for any G, at least 2, if you consider this donut with G number of holes, there is a closed hyperbolic surface which topologically looks like this donut with G number of holes. And moreover, if you consider collection of all closed hyperbolic surfaces which look like this donut with G number of holes up to isometry, it's a huge space. So this is diffeomorphic to R to the 6G minus 6. Okay? So you not only have infinitely many of them, you have a continuous family, uncountably many continuous family of many, many closed hyperbolic surfaces. So she has many choices for her next journey. Okay, so now I have to tell you what is the Euclidean line in a closed hyperbolic surface. So again, so in H2, so I'll first tell you what is Euclidean line in H2, and then my line in the closed hyperbolic surface will be image of the line under the quotient map as before. So in the apart space model, so my Euclidean line will be simply this horizontal line, y is equal to 1. Okay? So this is my apart space model, and then I look at this horizontal line, and this will be my Euclidean line. But in geometric space, all the objects actually, which are isometric to each other, they should be given the same name. Okay? So not only this is a Euclidean line, but all of actually isometric images under the action of isometric group PSL2R, they should be also called Euclidean lines. Okay? And what are the isometric images of this horizontal line? So they are either another horizontal line, but possibly with a different height, or it will be a circle which is tangent to the boundary. Okay? So these are Euclidean lines in hyperbolic plane. And another nickname for Euclidean line is a horocycle. So horocycle means that it's an imaginary circle. So this one actually looks like a circle, right? But however, it's not a circle in hyperbolic plane because the boundary is not a part of the hyperbolic plane. So this circle doesn't exist in hyperbolic plane because this point is not in my H2. So it's only imaginary circle. So that's what we call it horocycle. Okay, so then as before, right, so by Euclidean line on this closed hyperbolic surface, I simply mean the projection of Euclidean line in H2 under this canonical quotient map. Okay? So by the way, so when I talk about this quotient, H2 mod gamma, it means that every point in the same gamma orbit should be one point in the quotient space. So that's what quotient means. Okay, so where does now Euclidean traveler get to visit in this hyperbolic surface? So if she travels along Euclidean line, so which places does she get to see? So now let's think about the fundamental domain, again, for this regular octagon. But I'm going to now think of this picture in the apop space model. So this is my quotient map, and this is my fundamental domain for the regular octagon in the apop space model. So okay, it looks strange that why actually, so this one and then this one have the same size, right? I said it's a regular octagon. But again, in a pop space model, because we are dividing the Euclidean metric by the height, so when you are close to x-axis, actually, so this length is much larger than it appears. So you have to really think that this is a regular octagon. So they all have the same hyperbolic size, okay? Okay, so now she travels along this Euclidean line, okay? And as before, when she reaches the boundary of this fundamental domain, she gets instantly moved to another side by the side pairing transformation. And this side pairing transformation also moves this horocycle or Euclidean line to another Euclidean line. And then she must travel along this Euclidean line until she reaches another side of the fundamental domain. And then she gets moved somewhere else by another side pairing transformations and so on. Okay? So it looks a little bit more complicated than the Euclidean torus case. Okay? So nevertheless, it's a theorem of Hedlund in 1936. Any Euclidean line in a closed hyperbolic surface is dense. Okay? So no matter where you start, okay? No matter where you start, if you travel along the Euclidean line, she's guaranteed to see the whole space, the whole closed hyperbolic surface. Okay? So your travel guide can tell you, okay, you can start anywhere you want, but you will eventually see the whole world, whole space.
Do you make any assumption about some linearity of the moduli space?
No. Yeah.
Any point.
For any point. That's exactly the point. Yes. So I want to emphasize here, actually, it's very important that she travels along the Euclidean line. Okay? She has to be Euclidean traveler. Because if she travels along the hyperbolic line, then she is not guaranteed to see all the places. Generically, you will see all the places, but not all the time. Because some hyperbolic lines, some geodesics actually can accumulate only in some part of the hyperbolic, some part of the closed hyperbolic surface, but it does not go to everywhere. Okay? Yeah, so sometimes, yeah, if you want to enjoy your sightseeing, you should not insist going in the fastest way. If you just insist going fastest way, then you may not be able to see all the places. Okay, so how does Hedlund prove his theorem about actually, so if you travel along Euclidean lines, you see all the places. So I would say he goes upstairs. So what do I mean by upstairs? So we have identified H2 with the quotient of PSL2R by this compact group SO2. Okay, so PSL2R acts on H2 by isometric action. But this action extends to the action on the unit tangent bundle. So by unit tangent bundle, I simply mean the bunch of tangent vectors of norm 1 in the hyperbolic space. Okay? So PSL2R send this arrow to another arrow, so isometric action extends to the unit tangent bundle. And now this time there is no stabilizer, because if you think of this upward normal vector at I, the stabilizer of this normal vector must stabilize I first, so it means that it has to be a rotation if you want to stabilize this vector. But if you want to keep this normal vector as it is, you cannot rotate. So which means that the stabilizer of PSL2R on the unit tangent vector is so trivial. So which means that we have the identification of the unit tangent bundle of H2 with PSL2R without any quotient. So the group PSL2R can be really thought as a bunch of tangent vectors on H2. Okay? So now if you think about this group, so this is a one-dimensional group consisting of this triangular matrix 1T01. So it's a one-dimensional group. And this group will act on this PSL2R by translations on the right. You can multiply any PSL2R matrix by this matrix on the right. Okay? And what is the point about actually bringing this group U? So the point is that this U will tell you, actually, so this will trace out exactly my Euclidean lines. So for instance, if you consider this unit normal vector here, okay, so because this is a tangent vector, so this vector is an element of PSL2R. And if I look at the orbit of this vector under U, then I get all the upward normal vectors on this Euclidean line. So I recover the Euclidean line here. And for instance, if I look at this tangent vector, then its U orbit will give me all the inward normal vectors lying on this horocycle. Okay? So the U orbit traces out exactly my Euclidean lines. Okay? And actually, this picture can be moved actually when I quotient the picture by gamma. So remember, so we have identified H2 by this single quotient PSL2R mod SO2, which means that my closed hyperbolic surface is a double quotient of PSL2R, one side by gamma, one side by SO2. And then my Euclidean line lives here, right? But now when I go upstairs, so now the unit tangent bundle of my hyperbolic surface now becomes a single quotient, PSL2R mod gamma. And then here I have my U orbits, my orbit of the subgroup, and then this orbit of the subgroup project to Euclidean lines. So this is the reason why we go upstairs, because when I have a double quotient, I cannot act. Okay, I cannot multiply U and then get an action here. But when I go upstairs here, so because I can multiply any element of PSL2R from the right, I get a subgroup action on this space, on this homogeneous space. So this is why we go upstairs to see the action of a group. Okay? So then understand actually the close of the Euclidean line. It suffices to understand what is the close of the U orbit in the unit tangent bundle. Okay? So now you can imagine, so she was traveling along the Euclidean line, but now actually she's holding an arrow on her hand, and then she's traveling with the arrow. Okay? And now the Hedlund theorem says that, so even upstairs, actually, every U orbit becomes dense. Okay? So not only on the hyperbolic surface, but for any point x, for any arrow, the closure actually gives you not only all the places, but also all the possible angles. So you can see actually from the traveler's point of view, not only actually she gets to visit all the places, but she gets to appreciate actually all the objects from all possible angles. Okay, so now we move to the higher dimensional hyperbolic manifold. So again, I use a pop space model. So Hn is the half of the Euclidean n space. So I have x1 to xn minus 1, but last coordinate I denote by y, and then with positive y. So we just have the above the half space. And then again, the hyperbolic metric is the Euclidean metric divided by the height, Euclidean height. And geodesics, again, look like vertical lines or the circles, semicircles intersecting the boundary, which is now x1 to xn minus 1 plane orthogonally. So now this time isometry group, or the group of orientation preserving isometries of H1, Hn. So this is a special orthogonal group of signature n, 1. Okay, so I told you before, the orientation preserving isometries of H2 is PSL2R, and now this time I'm saying it is SO2, 1. Okay? But SO2, 1 and then PSL2R, they are isomorphic to each other. So I'm being consistent. And And Hn, the hyperbolic space, is now the quotient of its isometry group by this compact group SON. Okay? So we think of compact group, small group, so it's again almost the same as its isometries. And any closed hyperbolic N manifold, you can think of this as a definition. It's the quotient of Hn by a discrete co-compact subgroup of the isometry group of Hn. So this is what closed hyperbolic N manifold is. Okay? So in the dimension 2 case, we have seen continuously many, like uncountably many closed hyperbolic surfaces, but in higher dimension, so when n is at least 3, we only have countably many closed hyperbolic N manifold. So in higher dimension, it's much rarer to have the closed hyperbolic N manifold. So this is due to local rigidity theorem of Selbel-Calabi-Weil. But nevertheless, there are infinitely many closed hyperbolic N manifolds. So she has places travel. So she wants to travel. So now, what is the Euclidean line? Again, I have to tell you what's the Euclidean line. So in the half space model, so you consider this horizontal plane given by the height 1, y is equal to 1. And then any line on this horizontal plane will be called the Euclidean line. And so are their images under the isometry groups. The images will be, again, some circles tangent to the boundary or another horizontal lines. So these are Euclidean lines. And then she travels along this Euclidean line. And in this closed hyperbolic N manifold, so what is she going to see? So what are the possible closures of Euclidean line in this hyperbolic N manifold? Okay, so in fact, so this was answered by Marina Ratner, but her theorem is much more general. So I want to explain what Ratner theorem is in a general context. So in general, so let's say G is a simple Lie group. Okay. So you don't have to know the general definition. So just think of, say, SLNR is the n by n matrices with determinant 1. Or for our setting, so the relevant group is this special orthogonal group, SOn, 1. And let gamma be any discrete subgroup. Okay? Then you can consider this quotient space G mod gamma. Since gamma is a discrete subgroup, G mod gamma looks locally like G. Okay? And it's a homogeneous space because any 2 points can be moved from one to another by an element of G. So you have this homogeneous space. And now if you have any subgroup U of G, then you will act on this G mod gamma by translations on the right. So this is the homogeneous space with lots of actions coming from the subgroups of G. Okay? So the question is that for given any point x in this homogeneous space G mod gamma, you can ask, can you describe the closure of the U orbit? So this looks like a very simple question. You have G mod gamma. What is the closure of the U orbit? So there is a theorem called Morse-Algatistic theorem, which says that if your space has a finite volume, so we've been talking about the compact case, but okay, we can even allow finite volume because there are non-compact spaces with finite volume. So if your space is compact, or more generally, if it has finite volume, and if your U, your subgroup is a non-compact group, then for almost all, this is what Hiroshi asks, for almost all points, your orbit will be dense. Okay? So generically, no matter where you start, you will be see all the places G mod gamma. But however, this is very bad news for our traveler because the travel guide cannot tell you where you must start. It just says that where maybe randomly, but then she doesn't know where to begin because she's not guaranteed to see all the places. So this is exactly fixed by Ratner theorem. So Ratner theorem is that suppose I have a finite volume space G mod gamma. And here what is very important is this condition that we don't allow all the subgroups of G, but we only consider subgroup U, which is a subgroup generated by unipotent elements. This is why I wrote U. So we only allow subgroup generated by unipotent elements. And what is the unipotent element? A matrix is unipotent. It simply means that all of its eigenvalues are equal to 1. So this one, 1, T, 0, 1, the eigenvalues are all equal to 1, right? So this is a definition of a unipotent matrix. And yeah, so you just want to know that your subgroup can be generated by matrices with all eigenvalues 1, then in that case, for any starting point x in G mod gamma, your orbit will be, the closure of your orbit will be another homogeneous space of some closed subgroup. Okay? And note that this is as best as you can do because there might be some closed H orbit, intermediate closed H orbit, and then if you start in there, then you don't get out. Okay? But however, this is like this multidimensional case of the Kronecker theorem, but these are all the possibilities. So either your closure is everything, or you are another smaller homogeneous space. Okay, so this is what her theorem says.
Is the unipotent condition sufficient? Is it also necessary?
Necessary is a tricky question, but yeah. There are cases which people believe it has to be true, but under more conditions. But her theorem is about this. But the point is that we are not asking you to be unipotent, but you to be generated by unipotent elements. For instance, SLNR is not unipotent, but it is generated by unipotent elements. So you can apply to any connected simple group with no compact factors because they are always generated by unipotence. Okay, so now let's go back to our closed hyperbolic N manifold. So how does this Ratner theorem apply to our setting? So remember, so I had this closed hyperbolic N manifold Hn mod gamma, and then we are interested in Euclidean line, the close of the Euclidean line. So this time, not only going to the unitangent bundle, but we'll go to all the way up to the frame bundle, okay? Because the homogeneous space, the quotient of the isometry group is SO n, 1 divided gamma. So this is the frame bundle, not only the unitangent bundle. Okay? So we pass to the frame bundle. Then as before, the Euclidean lines are traced by this orbit of the one-parameter unipotent group. So you don't have to know actually how this complicated group look like, but I wrote it just to show you that this is unipotent. The eigenvalues are all equal to 1. Okay? So I have this one-dimensional unipotent group, and then if you understand the closure of this U orbit upstairs in homogeneous space G mod gamma, where G is the isometry group of Hn, so that will tell us what's the closure of the Euclidean line in the manifold. Okay? So we can apply her theorem to the frame bundle, and then this is a consequence of theorem. So for any closed hyperbolic N manifold, the closure of the Euclidean line is always another closed hyperbolic submanifold. So in dimension 2, it was all the time dense, but then in higher dimension, you can have intermediate closed hyperbolic manifold. Okay, but that's all there it is. But here is one small caveat. So I have to allow this transformation, what we call tilting. So this kind of corresponds to translation in the Kronecker theorem. So remember, when the line does not pass the origin, we had to allow translations. So this tilting is an operation in hyperbolic space, which kind of corresponds like hyperbolic translation. It's a natural operation which appears in this context. So special case of this theorem, when n is equal to 3, says that in a three-dimensional closed hyperbolic manifold, Euclidean line, because if n is 3, then you have actually only two possibilities, either dimension 2 closed hyperbolic surface or dense. So in this case, either the close of Euclidean line is some closed hyperbolic surface living inside the three-dimensional closed hyperbolic manifold, or orbit goes everywhere in the entire space. So you can think if she travels in the closed hyperbolic three manifold, she's guaranteed to see some hyperbolic space, either two-dimensional hyperbolic space or the entire hyperbolic space. And in fact, Ratner's theorem also tells you if you start from this point, then you will see two-dimensional closed hyperbolic world. Or if you have more time and if you want to enjoy the entire scenery, then you must begin somewhere. So it will tell you actually where you have to begin. So I want to emphasize somehow the surprising analogy of this theorem with the Kronecker theorem. So the Kronecker theorem says that the close of the Euclidean line is always subtorus modular translation. And then in this hyperbolic space, Ratner's theorem is the close of Euclidean line is another subworld of the hyperbolic world, but up to tilting. Okay, so now, so she has traveled to all the closed hyperbolic worlds. So now she wants to adventure to infinite hyperbolic world. Okay. So what about infinite volume hyperbolic manifolds? So will our traveler again be able to see some hyperbolic subworld? And the answer is no in general. So we do have, say, hyperbolic 3 manifold of infinite volume that you don't have this nice description of the close of the Euclidean lines. But however, we have this class of hyperbolic manifolds, what we call those with the Fuchsian ends. And in this class of hyperbolic manifolds, actually, we will have this so remarkable analogy with the Ratner theorem in this setting. So I want to explain, so what do I mean by hyperbolic manifold with Fuchsian ends? So let's start with the two-dimensional case, the surface case. So I start with some hyperbolic, so closed hyperbolic surface. And every closed hyperbolic surface has infinitely many simple closed geodesics. So closed geodesic means it's a geodesic which closes up, and simple means that it has no self-intersection. Okay, so it has infinitely many simple closed geodesic. So you take one simple closed geodesic, and then you cut along this hyperbolic surface along this simple closed geodesic, and then you obtain this compact hyperbolic surface now with a boundary component. Okay? You have this boundary component. And there is a canonical way, actually, to make this compact surface with the geodesic boundary into complete hyperbolic surface. Okay? So either you glue hyperbolic cylinder, or I would say you just leave it like in a hyperbolic world in a day or two, and it knows how to grow. So this is a so canonical way. It knows what it has to become. So this is what exactly hyperbolic surface with the Fuchsian end. Okay? Now in higher dimension, so now I have to say theorem first. So this is a Darbo's theorem, 2000. So if I have hyperbolic surface with the Fuchsian end, so clearly this has infinite area. Yeah? So this is the hyperbolic surface with infinite area. Then the closure of Euclidean line is either, so any Euclidean line is either closed or dense. Okay, so now what do you mean by here closed? Here closed does not mean it's a compact periodic. Here closed simply means that topologically closed. So in this case, it's simply proper isometric immersion of the Euclidean line. So this is my picture of the closed Euclidean line living in this hyperbolic surface with the Fuchsian end. Okay, so here, so this line lives inside the Fuchsian end, but it kind of disappears into infinity. Or the other possibility is that this Euclidean line will be dense everywhere, not only in this compact part, but everywhere. Okay. So now from the traveler's point of view, either she disappears to infinity, maybe, or she gets to see all the places. But again here, we know actually where to begin. If you want to disappear, maybe now she wants to retire. If you want to disappear, then you know where to begin. And then if you want to see the whole space, then you know where you have to begin. So we know exactly what the departure point has to be for this dichotomy phenomenon. Okay, so now we move to the hyperbolic manifolds with the Fuchsian ends, but in higher dimension case. So in higher dimension case, I already told you there are only countably, but still infinitely many closed hyperbolic n manifold. Okay, we have this countably infinitely many closed hyperbolic n manifold, and some of them have codimension 1 properly embedded hyperbolic surfaces, and then some of them don't. But there are infinitely many closed hyperbolic n manifold with codimension 1 hyperbolic submanifolds, like in this picture. So I have here hyperbolic n manifold, but I have here codimension 1 properly embedded hyperbolic submanifold. if I have such, then I can do this cut process again. So I can remove this co-dimension 1 hyperbolic submanifold, and then I obtain hyperbolic n manifold with this compact boundary. And again, there is a natural way to make this complete hyperbolic manifold. Okay? So this is what we call Fuchsian end. So if I start with actually, if I have actually several co-dimension 1 hyperbolic manifold which are disjoint from each other, we can do this process simultaneously with several of them. And then this is the cartoon of what I think of the hyperbolic manifolds with Fuchsian ends. Okay? No, finitely many, yeah. Right, so this is theorem I proved with McMullen-Mohammadi 2017 for n is equal to 3. And in higher dimension case, it was a joint work with my former student Lee. So let n be a now hyperbolic manifold with Fuchsian ends. Then the statement is that any Euclidean line is closed. Here closed means, again, it disappears into infinity, or the closure will be always another hyperbolic submanifold up to this tilting operation. Okay? So either you disappear or you get to see some hyperbolic subworlds, even in this infinite volume case.
Does this hyperbolic submanifold itself have Fuchsian ends?
A great question. Either, right, but then I allow empty Fuchsian ends.
Yes.
Yes, it is, yes. Okay, so I just want to indicate, so what's the difficulty of doing dynamics in infinite volume space? So what do you have to do moving from the finite volume to infinite volume? So when the space is compact, then when you consider the orbit of a subgroup, of course, since the ambient space is compact, the entire U orbit remains in a compact subset. Okay? But when you have an infinite volume, like in this picture, so when you consider the U orbit, so what does it mean? We want to understand the closure, right? By definition, closure means the set of accumulation points. So I want to see where the U orbit accumulates, but in the infinite volume, the problem is that it's very, very hard to see accumulation points because the U orbit will go out of this flare, and then it may come back, but it goes out again, and it may come back. But then in the end, it's going to spend actually 0 Lebesgue time inside your compact part, and it spends most of the time at infinity. So it's very, very hard to capture where it accumulates. So this is the somehow nutshell difficulty of doing dynamics in the infinite volume space. And in fact, actually, so what we had to work on is somehow the analysis on these fractals. So these hyperbolic manifolds, actually, I described to you. When you go to infinity, when you go to the geometric boundary, this is what you see. So dimension 3, and then higher dimension. And then understanding this recurrence, and then understanding this intermediate behaviors have to do with this analysis on fractals. Okay, so I hope I explained what this picture meant to you. Okay, so thank you.